In this section, we're going to discuss what's called the Fibonacci sequence and how it relates to the golden ratio. This is one of my favorite parts of 139. We find the Fibonacci sequence, which a sequence is just a series of numbers in all parts of life. A lot of them show up in nature. So if you look at the spirals in a flower, they are usually Fibonacci numbers, 34 and 21 being examples of Fibonacci numbers. Pine cones also have a similar spiral shape. In this particular pine cone, there are 18 spirals in one direction and 13 in the other, both Fibonacci numbers. Pineapples also using 5 spirals and 8. Those are also Fibonacci numbers. So if we look at these numbers that were in the spirals, we can see the Fibonacci pattern. The Fibonacci pattern starts with 1 and 1, and then from there you add the two previous numbers to get the next one. So for instance, 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. And this pattern can continue on forever. The Fibonacci sequence never stops. We can keep adding them together as much as we needed to. Fibonacci was a man who discovered this pattern. We knew about some properties of the golden ratio, but we didn't know where that ratio came from until he discovered this pattern and realized that the golden ratio is found by dividing Fibonacci numbers. Here again you see the pattern. The reason that nature likes to use these numbers is it has to do with the growth and packing of keeping the spirals as tightly wound as possible. We have a formula here to demonstrate what I just said about adding the two previous. A Fibonacci number is equal to the sum of the two Fibonacci numbers before it. So for instance, the 30th Fibonacci number is equal to the 28th plus the 29th Fibonacci number. The golden ratio that I spoke of earlier, which Fibonacci discovered was based off of these numbers, is found in art all over the place. Da Vinci loved the golden ratio. The golden ratio measures a rectangle. So it is said in Mona Lisa, he wanted her to have a proportioned nose, so he made it a golden rectangle. And from there we can build more golden rectangles. So her nose is a golden rectangle, and I just drew in the rest of them. Golden rectangles have a lot of neat properties. If you have one, you can find infinitely more bigger and infinitely more smaller than that one. And if you look at the ratio of their sides, the short side to the long side, that should be the same ratio of the Fibonacci sequence. The Greeks also knew about this golden rectangle, and a lot of their architect was based off of it. If you think about the board puzzles that kids learn their shapes on, where they have the little pegs, those are almost always golden rectangles, that shape. So you can see this whole Parthenon shape is a golden rectangle. Again, what makes it golden is if we measure the short side to the long side and divide those numbers, it's going to come out to a number called phi. Phi is the golden ratio. It's 1.6. And you find the same thing as if you take two of the Fibonacci numbers and divide them. We have other artists that have also used golden ratios in their painting. We have architects that also have enjoyed using the golden rectangle and the golden ratio. There are other examples of the same ratio, so lots of musical instruments have it. So take the violin for instance, if you compare this white part, the length of that, to this white part, that would give you the golden ratio. We have to be in these ratios in order for the instrument to make the correct sound.